4.2 The Transformer. Transformer is one of the most important electronic devices. I strongly recommend everyone spend lots of time learning transformer and becomes an expert on it. This is a typical transformer circuit. And this transformer has two sides. The one on the left connects to the power source, and we call it primary side. And the other side connects to the load is the secondary side. The electrical energy will be transferred from the primary side, the power source, wirelessly to the secondary side, the load. The schematic for a transformer is in the center of the circuit, between the primary and the secondary sides. As you can see, a transformer is made of inductors. In the symbol, it shows made of two inductors, one on the left, the other one is on the right. And between the two inductor symbols, there are two parallel lines. It represents the magnetic core. The electrical energy, the sine wave, will reach from the primary side to the secondary side wirelessly. And there are a few notations, such as above the transformer schematic symbol, you will see N1 column N2. The N here means the number of windings, number of turns for making that inductor. And the N2 is the number of turns of wires, the loops, for the secondary inductor. This is one of the most important factors can affect the kind of transformer. Whichever side has more turns, that side has higher voltage. For example, if the primary side inductor has 300 turns of wires or loops, and then the secondary side has 1,000 turns of loops of those wires. So the ratio is 300 to 1,000, or we can say is 3 to 10. So this is a step-up transformer. If the input equals to 3 volts, the output will be 10 volts. If input is 30 volts, the output will be 100 volts. The number of turns between both sides and their voltages are proportional, directly related. In terms of the mathematical expression is the primary side voltage V1 divided by the secondary side voltage V2 equals to the primary coil's turn number, N1 divided by the secondary inductor's turn number. We know the reason for using a transformer is to increase or decrease the voltage. In a more professional term, we say we are going to step up or step down voltages. Whichever side has higher number of turns, that will get higher voltage. Conversely, the side with fewer numbers of turns, it has lower voltage. This picture shows the meaning of the dotted notation. When we have the two dots at the same side, which means on the top in this case, the output waveform and the input waveform have the same polarity, which means when input voltage goes up, output voltage goes up too. If the input voltage goes down, the output voltage goes down simultaneously. The phase dots showing at the upper ends of the winding. The dotted ends have the same instantaneous phase. In other words, when a positive half cycle appears across the primary side, a positive half cycle appears across the secondary. On the other hand, the other dot is on the opposite side of the circuit. In this example, the dot of the secondary side is marked on the bottom, which is the opposite side of the primary sides. If you look at the input waveform, when it goes up and the output waveform goes down, And when the input signals goes down, the output signals goes up. The polarities are flipped. This picture shows how we can use a transformer with the diode circuits. We start reading this schematic from left towards right. On the left side, there is a power source. This power source has three outputs. One produces positive voltage, the other one produces the negative voltage. The one in the center connects to ground. On the primary side of this transformer, the inductor connects to the positive and the negative terminals. On the secondary side of this transformer, that inductor connects to a diode, and then the diodes connect to a load resistor to ground. The reason is that we use the transformer to reduce that 120 volts to a smaller voltage. That smaller voltage can go through the diode without burning the diode, and then the voltage goes to the load. Now let's work on example 4-2 on page 92. What are the peak load voltage and the DC load voltage in figure? Use the first approximation. To solve the problem, let's write down some important formulas for transformer. The most important formula is the one shows the relationship between the turn numbers and the voltages. That is, N1 over N2 equals to V1 over V2, where N1 is the primary side turn number. In this case, it's 5. And the secondary turn number N2 equals to 1. The ratio is 5 to 1. We don't need to have the exact numbers. The main thing that we need is their turn ratio. And then the other side is V1 over V2, where V1 is given. The primary side of the transformer is 120 volts, and we're looking for the output voltage, the voltage at the secondary side. So we have 5 over 1 equals to 120 volts divided by V2. Use cross multiplication to rearrange the equation. We know 5 times V2 equals to 1 times 120 volts. That's called a cross multiplication. After rearranging it and find the equation for V2, we get V2 equals to 120 volts over 5, and that's 24 volts. So the secondary side voltage of the transformer is 24 volts. That 24 volts provided to the diode and that resistor together. We know the 120 volts coming from the original source is root mean square voltage. Therefore, this V2 is also root mean square voltage. In order to find the peak voltage, we use that formula. The root mean square voltage equals to 0.707 times the peak voltage. Rearrange this equation, the peak voltage equals to the root mean square voltage divided by 0.707. And plug in the root mean square voltage, which is 24 volts over 0.707, we get a 34 volts. This is the peak voltage at the transformer's secondary side. We already got the peak load voltage, that's 34 volts. We know the output of this diode circuit, the half-wave rectifier circuit, is the one showing on this figure. And to find the average value, which is the DC voltage, we use the formula Vp over pi, where this Vp is the voltage after the diode. Because we are using the first approximation, the diode doesn't cause any voltage. There is no 0.7 volt involved. Therefore, the entire 34 volts will be the output of the diode. In other words, the resistor RL receives 34 volts. So plug this back to the formula, 34 volts divided by pi, that equals to 10.8 volts. So in conclusion, the DC load voltage equals to 10.8 volts. Now we are going to solve the same problem using second approximation. With the second approximation, we need to consider the voltage drops on the diode. And by default, this is 0.7 volts. Therefore, the voltage coming out from the secondary side of the transformer, 34 volts, need to remove that 0.7 volt on the diode. And the remaining voltage is the voltage applied to the load resistor RL. This equals to 33.3 volts. We use the Vp over pi again to find the DC voltage. So in this case, we use 33.3 volts divided by pi and punch these numbers into the calculator. It's 10.6 volts. Let's compare both output waveforms, the one using the first approximation and then this one with second approximation. The figure on the left shows the voltage across the resistor by using the ideal diode. As you can see, the output voltage starts from 0 volts and then continuously reaches to 34 volts and then drops to 0 volts, becomes flat for a certain amount of time, and the second cycle begins. On the right-hand side, this is for using the second approximation. V2 need to reach to 0.7 volt, and then the diode start to conduct. As soon as the diode start to conduct, current shows in the wire. And as soon as the current start flow through the wire, there's voltage drops on RL. That's V out.